Oops. All right. Proposition 17 says, in any triangle, two angles taken together in any manner are less than two right angles. So it's a pretty straightforward proposition. Take any triangle, take any two angles of that triangle, add them together. It's going to be less than two right angles. For us today, this is a really kind of an obvious one because we know that in Euclidean geometry, the sum of the internal angles is 180 degrees, which is two right angles. So yeah, obviously, if you chop off one of those angles, no matter how small that angle might be, the remaining sum of the other two angles is going to be less than 180 degrees, or less than two right angles. So, all right, let's jump in and prove this proposition, which, without looking ahead, I imagine is going to be quite important when we do want to prove that the internal sum of the angles of a triangle is 180 degrees. So here's our triangle. I kind of already started. I sort of did the first step already, sort of by accident when I was making the diagram. So, proof. Step 1, extend BC to D. And maybe at the outset here, too, well, no, it doesn't need to be stated at the outset. So what we're going to do, though, by the way, is that we're going to prove that, in particular, angle ABC and angle ACB, the sum of those two, is less than two rights. But it's kind of like a without loss of generality situation, that because we prove it for those two angles, it applies to any pair of angles because you can just use the same argument. So I was thinking about stating that here at the outset, but I think I'll just say that at the end. Okie dokie. So we've extended BC to D. If you want to justify that, that is postulate 2 that allows us to do that. Just make any line longer. That's what postulate 2 says, is that's always legal. All right. Well, if that's the case, then now we've created this new angle, ACD, and we previously, just our last proposition, told us that this angle, ACD, is greater than either of the interior and opposite angles. In particular, then, it's greater than angle ABC. So by proposition 16, we know that angle ACD, which is this external angle, is greater than, specifically, angle ABC. Oops, I want to justify that. That needs some justification, more than the extending. Oh, I already did. Come on, why didn't you guys tell me? All right, that's what happens. It's kind of a weird thing where what you say and what you write are sometimes two different things. Right. Okay. So, well, if this is the case, then by proposition 16, this is the case. Well, if this inequality holds, then we can add the same thing to both sides of the inequality, and the inequality still holds. So, it's the case that angle ACD, and if I add to both sides, if I add angle ACB, the inequality holds. So angle ACD plus angle ACB is greater than angle ABC plus angle ACB. Right? And that just follows. We don't even really need to justify that. Is that justified? No, that's just kind of. Maybe that should somehow be justified. I think it follows from one of the common notions that like equals added to equals are equal. I think that it falls from that, but I'm not quite sure. Like that seems to me like something that today we might be like, we maybe should have something in place to make sure that that's true. But it's pretty intuitively obvious. Okie dokie. Right, but we know that angle ACD, this right-hand side, or sorry, left-hand side, angle ACD, which is right here, plus angle ACB, that is two rights. So angle ACD plus angle ACB equals two right angles. And that was by Prop 13 that said that. So, therefore, the result follows because this left-hand side right here, we said, well, that is two right angles, and that is greater than angle ABC plus angle ACB. So, therefore, two right angles is greater than angle ABC plus angle ACB. Right, and we can similarly prove this true for any pair of angles. And that's that. QED, therefore, etc.